Well, welcome back. This is flip-flops 5. We're going to introduce the D flip-flop. Well, here's our truth table and our logic symbol of our D flip-flop. You can see that it's much simpler and much more basic than the clocked RS. D flip-flops are sometimes called data flip-flops or a data latch, and that's because they hold on to data or hold on to something. And that data latch can store a signal, and that signal, if you think about data, is really just a binary bit, a 1 or a 0. So it can store it at its input D. And the timing of that storage is really dependent upon the clock. So that clock, just like the clocked RS, plays a very important role in this flip-flop in storing the data. Data latches must have a clock. So as you can probably guess, they are a synchronized type of flip-flop. So when that clock is inactive, the stored number remains unchanged. So what that means is that when the clock is in 0, the number that's inside the flip-flop doesn't change no matter what the data is at input D. And that's very much like the clocked RS. So I could change this input from 0 to 1 to 1 to 0, 0, 1 over and over and over. But if this is inactive here, if this is 0, then no new number will be stored inside the flip-flop. So when that clock becomes active, so when it goes from 0 to 1, whatever is at this point at D, so whatever number goes into this flip-flop, if it's a 1, will go in only when this clock becomes active. So it's very similar again to that idea of a synchronous flip-flop as we saw with the clocked RS. The clock then returns back to its inactive state or back to 0, and then the last value of Q is stored. This is a commercial D flip-flop, symbol over here and truth table on the left. We will be using this type of flip-flop to wire our large memory circuit. So you might want to take some notes down about this and maybe even write the truth table down because you're going to need it. The inputs on the right side here, you see you have the data, you've got the clock, you've got the Q and Q naught as your outputs, but you've got two additional inputs here. One's called preset, one is called clear. And the addition of those two inputs creates two different modes. So on this truth table here, you can see the inputs are divided up into asynchronous and synchronous, and that's what the preset and clear do. So whenever we have preset is set to 0 and clear is 1, it doesn't matter what the clock or D is. It actually overrides that functionality, which is why there's an X there. Q is automatically 1, which means it's in the set mode. But we call that asynchronous set because it is completely independent of the clock. Similarly, if preset is set to 1 and clear is set to 0, then it overrides the clock, but it puts us in the reset mode. And again, not synchronous reset, but an asynchronous reset because we're not dependent upon that clock at all. Prohibited, as we know, means that Q and Q naught are on at the same time, which we can't have, and that would be a 0, 0, which would be a bad thing to have happen, and it's considered an illegal state. And again, but it overrides the clock functionality here. So if you look back at the previous slide, you'll see that if preset and clear are both 1, it's really just what we saw in the last slide. All it is saying that when D is at a 1 and the clock is activated, and it goes back down to 0, that D, which is 1, will be stored inside the flip-flop at Q. Okay, it'll be output there. Likewise, if we have 0, then it will be a result of 0, and that's why we have the set and reset modes here. Okay, you also notice one other thing here. The clock has this little triangle here. That means that it is a positively edge-triggered flip-flop. So whenever you see that symbol, you'll know that it's positively edge-triggered. The negatively edge-triggered has the same little symbol there, except it has an inverter right here, which I'm sort of magically drawing here with my mouse. Okay, so that concludes our D flip-flop video, and we will continue on with another one later.